In a world built on polymers, these versatile materials are everywhere, seamlessly integrated into our daily lives. From the moment we wake up and reach for our phones to the clothes we wear and even the cars we drive, polymers are an essential part of our existence. Polymers also make up much of the world around us, from the plastic in our phones to the fibers in our clothes. They are the unsung heroes of modern technology, providing the materials needed for innovation and convenience. Imagine a world where the materials we use are designed to degrade safely and efficiently, reducing waste and minimizing our impact on the planet. This is the promise of controlled polymer degradation, a new beginning for both science and society. Gamma rays, a type of high-energy electromagnetic radiation, have the ability to penetrate deep into materials, interacting with the very building blocks of matter. Hello and welcome to my channel. My name is Salah Lotfy, and today I'd like to take you on a brief journey into my scientific work and achievements. In 2009, my research titled Controlling Degradation of Low Molecular Weight Natural Polymer Dextrin Using Gamma Irradiation was published in the International Journal of Biological Macromolecules. This study marked a turning point in my career, demonstrating the potential of radiation chemistry to enhance natural polymers' properties. What truly humbled me was how this research gained recognition. From 2009 to 2016, I consistently received reports from BioMedLib that my work was ranked among the top 10 studies in its field. These reports reflected how my findings influenced global research on topics like radiation's impact on natural polymers and environmental applications. Every acknowledgement reinforced my gratitude and commitment to meaningful science.
Dextrin is a natural polymer. It comes from starch, which is a complex carbohydrate found in many plants. This natural polymer has been utilized for centuries, and its applications have only expanded with modern science. Starch is found in plants like corn and potatoes. These plants are cultivated worldwide, making dextrin an accessible and sustainable resource. The process of extracting starch from these plants is both efficient and environmentally friendly. Dextrin is used in many things we use every day. From the food we eat to the medicines we take, dextrin plays a crucial role. It acts as a thickening agent, a stabilizer, and even a binding agent in various products. It is in food, medicine, and even glue. In the food industry, dextrin is used to improve texture and shelf life. In pharmaceuticals, it helps in the controlled release of drugs. In adhesives, it provides strong bonding properties. Dextrin is made of small sugar molecules. These molecules are linked together in a specific structure, giving dextrin its unique properties. The arrangement of these sugar molecules determines how dextrin behaves in different applications. These molecules can break down over time. This process is influenced by factors such as temperature, humidity, and pH levels. Understanding this breakdown is essential for improving the stability and performance of dextrin-based products. This breakdown is called degradation. Degradation can affect the effectiveness of dextrin in various applications. Scientists study this process to develop methods to slow down or prevent degradation, ensuring that dextrin remains functional for longer periods. Degradation can change how dextrin works. For instance, in food products, it can alter texture and taste. In pharmaceuticals, it can affect drug delivery. Therefore, controlling degradation is crucial for maintaining the quality and efficacy of dextrin-based products. Scientists want to control degradation to keep dextrin useful. Through innovative research and advanced technology, they are developing new ways to enhance the stability of dextrin. This ongoing research ensures that dextrin continues to be a valuable resource in various industries. Gamma rays are a type of energy. They are invisible to our eyes. Gamma rays can pass through many materials. They can change the structure of materials. This makes them useful in many fields. Scientists use gamma rays to sterilize medical equipment. They also use them to preserve food. In this study, we used gamma rays to modify dextrin. We found that gamma rays can control the degradation of dextrin. By exposing dextrin to a specific dose of gamma rays, we could slow down its breakdown. This was a major breakthrough. Controlling degradation means we can make dextrin last longer. This has many benefits. For example, it can make medicines more effective. It can also make food safer to eat. Section 4. Impact and Recognition, a Legacy. Our journey began with a simple question, but it has led to groundbreaking discoveries that have left an indelible mark on the scientific community. Our research has been recognized worldwide. From prestigious awards to heartfelt congratulations from peers, the impact of our work is felt far and wide. It has been published in prestigious scientific journals. These publications serve as a testament to the rigorous and innovative nature of our research, inspiring others to follow in our footsteps. It has also been presented at international conferences. These platforms have allowed us to share our findings with a global audience, fostering collaboration and sparking new ideas. This research has paved the way for new studies. Each experiment, each discovery builds upon the last, creating a foundation for future breakthroughs. Scientists are now exploring the use of gamma rays to modify other natural polymers. This innovative approach opens up new possibilities in materials science, potentially revolutionizing various industries. This is an exciting time for the field of radiation chemistry. Imagine a world where we could control the very building blocks of nature. Imagine harnessing the power to manipulate molecules, enhancing their properties for the benefit of humanity. This isn't science fiction, it's the exciting reality explored by scientists like Salah Lotfy. At the heart of Lotfy's research lies a humble yet powerful molecule, dextrin. Dextrin, a natural polymer derived from starch, is a workhorse in various industries. From food and pharmaceuticals to textiles and adhesives, its applications are vast. But what if we could enhance dextrin's properties, making it even more versatile and beneficial? This is the question that drove Lotfy's groundbreaking research. Lotfy's study delves into the fascinating world of gamma irradiation and its impact on dextrin. Gamma rays, a form of high-energy electromagnetic radiation, are often perceived as dangerous. However, under controlled conditions, they can be harnessed as a powerful tool for modification. Lotfy's research unveils the potential of gamma irradiation to control the degradation of dextrin, unlocking a world of possibilities. Gamma irradiation might sound like something straight out of a superhero comic, but it's a well-established technique with numerous applications. In the realm of science, gamma rays are used for sterilization, food preservation, and even cancer treatment. How can something so powerful be used so delicately? The key lies in controlling the dosage and exposure time. Lotfy's research highlights gamma irradiation as a gentle modification technique for dextrin. By carefully calibrating the irradiation process, he demonstrated that it's possible to alter dextrin's molecular weight without causing unwanted side effects. Imagine a sculptor meticulously chiseling away at a block of marble, revealing the masterpiece within. Similarly, gamma irradiation, when precisely applied, can refine dextrin's properties, enhancing its stability, solubility, and biodegradability. This level of control opens up exciting possibilities for tailoring dextrin to specific applications. Picture a future where biodegradable plastics replace their polluting counterparts, where drug delivery systems target diseases with pinpoint accuracy, and where sustainable agriculture practices nourish our planet. This is the promise of Lotfy's research. By controlling dextrin's degradation through gamma irradiation, Lotfy paves the way for its use in a wide range of fields. In medicine, modified dextrin can be used to create biocompatible and biodegradable drug carriers, delivering medications directly to targeted cells and minimizing side effects. Imagine targeted cancer therapies with fewer side effects or time-released medications that improve patient compliance. The benefits extend beyond medicine. In agriculture, modified dextrin can be used to develop biodegradable films for controlled-release fertilizers and pesticides, reducing environmental impact while boosting crop yields. The possibilities are truly endless, with potential applications in environmental remediation, water treatment, and beyond. Section 4. Salah Lotfy, a scientist's journey of discovery. Behind every scientific breakthrough lies the dedication and passion of researchers driven by a thirst for knowledge. Salah Lotfy's journey exemplifies the spirit of scientific inquiry, marked by curiosity, perseverance, and a commitment to making a difference. Lotfy's fascination with polymers and their potential applications led him down a path of exploration. He recognized the versatility of dextrin and sought to unlock its full potential. His research on gamma irradiation wasn't just about scientific advancement, it was about finding solutions to real-world problems. This groundbreaking research has not only advanced our understanding of dextrin and gamma irradiation, but has also inspired a new generation of scientists. Lotfy's work serves as a testament to the power of curiosity-driven research and its ability to shape a better future. Section 5. A brighter future, shaped by science. In a world grappling with challenges such as pollution, disease, and food security, science offers a beacon of hope. Salah Lotfy's research on controlling dextrin degradation through gamma irradiation is a shining example of how scientific innovation can pave the way for a brighter future. By harnessing the power of this technology, we can unlock the full potential of dextrin, creating sustainable solutions in medicine, agriculture, and beyond. As we delve deeper into the intricacies of the molecular world, we discover new possibilities and innovative solutions to the challenges facing humanity. Let Lotfy's journey inspire us all to embrace the power of science and innovation. By supporting scientific inquiry, fostering collaboration, and nurturing the next generation of thinkers, we can create a world where science fiction transforms into a beautiful reality.
The dance of polymers, life, breakdown, and new beginnings. We live in a world built on polymers. These versatile materials are everywhere, seamlessly integrated into our daily lives. From the moment we wake up and reach for our phones to the clothes we wear and even the cars we drive, polymers are an essential part of our existence. These long chains of molecules are the building blocks of life, forming the very essence of our DNA and the proteins that make us who we are. They are fundamental to biological processes, ensuring that life, in all its complexity, can thrive and evolve. But polymers also make up much of the world around us, from the plastic in our phones to the fibers in our clothes. They are the unsung heroes of modern technology, providing the materials needed for innovation and convenience. Like all things, polymers have a life cycle. They are created, they serve their purpose, and eventually, they reach the end of their useful life. This cycle is a natural part of their existence, mirroring the cycles we see in nature. They are born, they age, and they eventually break down. This process of degradation is inevitable, but it is also a critical aspect of the polymer life cycle. It ensures that materials do not last forever, which can be both a challenge and an opportunity. This process of breakdown, known as degradation, can happen naturally due to exposure to light, heat, or even just the passage of time. Environmental factors play a significant role in how quickly and effectively polymers degrade. But what if we could control this degradation? What if we could design polymers that break down in a predictable and controlled manner? This would revolutionize how we manage waste and recycle materials. What if we could harness the power of science to influence how polymers age and change? By understanding the mechanisms behind polymer degradation, we can develop new materials that are more sustainable and environmentally friendly. This is where the fascinating world of gamma irradiation comes into play. Gamma rays can be used to alter the molecular structure of polymers, making them more or less susceptible to degradation. This technology opens up new possibilities for creating materials with tailored lifespans. By understanding and manipulating the breakdown of polymers, we can unlock incredible possibilities for innovation and sustainability. This knowledge allows us to create materials that not only meet our needs but also align with our environmental goals, paving the way for a brighter and more eco-conscious future. Imagine a world where the materials we use are designed to degrade safely and efficiently, reducing waste and minimizing our impact on the planet. This is the promise of controlled polymer degradation, a new beginning for both science and society. In the vast world of polymers, dextrin stands out as a versatile and intriguing character. It's a natural polymer derived from starch, a carbohydrate found abundantly in plants like corn, potatoes, and rice. Dextrin is prized for its adhesive properties, making it a key ingredient in a surprising range of everyday products. Think of the glue on envelopes, the binding agent in pills and tablets, or even the sticky coating that holds the sugar on donuts. But dextrin's talents don't stop there. It also plays an important role as a thickening agent in food, textile, and paper industries. Its ability to control viscosity and improve texture makes it an indispensable ingredient in countless products we encounter daily. Imagine a world invisible to the naked eye, a world of atoms and molecules in constant motion. This is the realm where gamma irradiation works its magic. Gamma rays, a type of high-energy electromagnetic radiation, have the ability to penetrate deep into materials, interacting with the very building blocks of matter. When these rays encounter polymers like dextrin, they trigger a fascinating dance of energy transfer. This interaction can cause the polymer chains to break apart or link together in new and unexpected ways. This ability to modify the structure of polymers makes gamma irradiation a powerful tool in the hands of scientists and engineers. It's like having a microscopic toolkit that allows us to fine-tune the properties of materials with incredible precision. Section 4: Free radicals, the tiny architects of change. At the heart of gamma irradiation's effects on polymers like dextrin lies the intriguing world of free radicals. These tiny yet powerful entities play a crucial role in the transformation of materials at the molecular level. Understanding their behavior is essential for harnessing their potential in various scientific and industrial applications. Free radicals are highly reactive species, characterized by their unpaired electrons. These unpaired electrons make them incredibly eager to engage in chemical reactions, acting like tiny sparks of energy. They are always on the lookout for other molecules to bond with, driving a myriad of changes in the materials they interact with. When gamma rays interact with dextrin, they impart enough energy to knock loose electrons from the molecules. This process initiates a cascade of free radicals within the material. The energy from the gamma rays disrupts the stable structure of dextrin, creating numerous reactive sites. These newly formed radicals do not remain idle. They interact with each other and with the surrounding polymer chains, leading to a complex series of reactions. The interactions can vary widely depending on the specific conditions and the nature of the polymer. One possible outcome of these interactions is the breaking apart of dextrin chains, a process known as degradation. This can lead to a reduction in the molecular weight of the polymer, altering its physical properties significantly. On the other hand, free radicals can also encourage the polymer chains to link together, forming a more interconnected network. This phenomenon, known as cross-linking, can enhance the strength and stability of the material, making it more suitable for certain applications. The delicate balance between degradation and cross-linking is key to understanding how gamma irradiation can be used to tailor the properties of dextrin for specific applications. By controlling the irradiation conditions, scientists can fine-tune the material's characteristics, optimizing it for uses ranging from medical devices to food packaging. This ability to manipulate the molecular structure of polymers opens up a world of possibilities, showcasing the profound impact of these tiny architects of change. Section 5: Unveiling the secret structural and thermal transformations. To truly grasp the impact of gamma irradiation on dextrin, we need to delve into the world of structural and thermal analysis. This involves a series of meticulous experiments and observations that reveal the hidden changes occurring at the molecular level. Scientists use sophisticated techniques to study how the arrangement of atoms within dextrin molecules changes after irradiation. These techniques allow researchers to visualize and understand the complex interactions and rearrangements that take place. X-ray diffraction, for example, reveals the intricate crystalline structure of dextrin. By analyzing the diffraction patterns, scientists can determine how the crystal lattice is altered by gamma irradiation, providing insights into the material's structural integrity. Spectroscopy methods like FTR or Fourier transform infrared spectroscopy provide insights into the types of chemical bonds present. This technique helps identify specific functional groups and monitor changes in the chemical composition of dextrin. These techniques paint a detailed picture of the molecular transformations taking place. By combining data from different analytical methods, scientists can construct a comprehensive understanding of how gamma irradiation affects dextrin at the molecular level. Thermal analysis methods such as thermogravimetric analysis or TGA shed light on how dextrin's thermal stability and degradation behavior are affected by irradiation. TGA measures the amount and rate of weight change in a material as it is heated, providing valuable information about its thermal properties. By studying the weight loss of dextrin as a function of temperature, scientists can determine how resistant the modified material is to heat. This information is crucial for applications where thermal stability is a key factor, such as in food packaging or biomedical materials. Understanding these transformations allows researchers to optimize the properties of dextrin for specific uses, ensuring it performs effectively under various conditions. Section 6. Dextrin's transformation-enhanced properties for real-world applications. The beauty of science lies not just in discovery, but in application. The insights gained from studying the effects of gamma irradiation on dextrin have paved the way for exciting real-world applications. By carefully controlling the irradiation dose, scientists can enhance specific properties of dextrin, making it even more valuable for various industries. For instance, gamma irradiation can improve the adhesive strength of dextrin-based glues, making them ideal for demanding applications. In the food industry, irradiated dextrin can exhibit improved solubility and thickening properties, leading to more stable and desirable textures in sauces, soups, and other food products. The ability to tailor dextrin's properties through irradiation opens up a world of possibilities for innovation across multiple sectors. Let us delve into the experimental framework used to study the degradation of dextrin under gamma irradiation. Dextrin, a natural polymer with diverse applications, was selected for this investigation to explore its physicochemical properties and structural changes upon exposure to radiation. The dextrin used in this research was sourced from Cisco research laboratories. It was a white powder with a sulfated ash content of up to 0.2% and reducing sugars capped at 4%. To examine the effect of irradiation, dextrin samples were packed in polyethylene bags and exposed to gamma rays using a cobalt-60 source at the National Center for Radiation Research and Technology in Cairo, Egypt. The irradiation dose ranged from 5 to 100 kilograms, applied at room temperature. Electron spin resonance spectroscopy was utilized to measure the free radicals generated during irradiation. Using a Bruker EMX spectrometer, the team recorded the spectra under specific conditions. A tiny sample of dextrin, approximately 0.1 grams, was centered in the spectrometer's sensing zone, revealing the radical activity as a function of irradiation. To understand the flow behavior of dextrin solutions, a cone plate rheometer was employed at 25 degrees Celsius. The study used power law and Bingham models to describe the rheological properties, revealing how irradiation impacts viscosity and flow characteristics. A sample preparation process ensured uniform dispersion involving sodium hydroxide, perchloric acid, and distilled water to achieve a neutral pH of 7. Thermal analysis was conducted using a Perkin-Elmer system with tests running from ambient temperatures up to 600 degrees Celsius. Differential scanning calorimetry helped determine critical temperature points. The structural impact of irradiation on dextrin granules was studied through a scanning electron microscope and X-ray diffraction. These tools revealed significant changes in surface topology and crystallinity. This comprehensive approach provided valuable insights into how gamma irradiation influences dextrin's structural and chemical properties. By employing advanced techniques, the research demonstrated gamma irradiation as an efficient and eco-friendly tool for modifying natural polymers like dextrin, paving the way for further industrial and biomedical applications. We're diving into the fascinating world of dextrin, a substance that might not be a household name, but plays a crucial role in our daily lives. You might not know it by name, but dextrin is everywhere. It's a versatile carbohydrate that finds its way into a myriad of products we use every day. It's in your food, your medicine, even the glue on your envelopes. Yes, that sticky stuff that keeps your letters sealed tight often contains dextrin. It's a jack of all trades, a true multitasker in the world of materials. Dextrin is a type of carbohydrate made from starch. Starch, as you might know, is a complex carbohydrate found in many plants. Think of it like this. Starch is the big, bulky parent, and dextrin is the smaller, more versatile child. When starch breaks down, it forms dextrin, which is easier to work with in various applications. We can use it to thicken soups, stabilize medications, and even improve the texture of baked goods. Its versatility makes it an invaluable ingredient in both the food and pharmaceutical industries. But what happens when we introduce gamma irradiation to the party? This is where things get really interesting. Gamma rays are like tiny bursts of energy, and they can have some pretty interesting effects on materials like dextrin. These high-energy rays can alter the molecular structure of dextrin, enhancing its properties. Think of it like giving dextrin a superpower boost. The gamma rays can make dextrin even more effective and versatile. Scientists are always looking for ways to improve materials, and gamma irradiation offers a unique tool. By exposing dextrin to gamma rays, we can create a material with enhanced properties that can be used in even more applications. We can use it to modify the properties of dextrin, making it even more useful for a variety of applications. This could lead to new innovations in food science, medicine, and even industrial applications. So buckle up, because we're about to explore the exciting world of gamma-irradiated dextrin. Stay tuned as we uncover the potential of this upgraded wonder material and see how it could revolutionize the way we use dextrin in the future. Now let's talk about free radicals. No, not those kind of radicals. We're talking about atoms and molecules. These tiny entities are the building blocks of everything around us, from the air we breathe to the food we eat. But when they become free radicals, they can cause quite a stir. When gamma rays interact with dextrin, they can knock some electrons out of whack, creating these unstable molecules called free radicals. Gamma rays are a form of high-energy radiation, and when they collide with dextrin molecules, they impart some of their energy to the electrons in these molecules. Think of it like a game of molecular tag. The gamma rays are the taggers, and the dextrin molecules are the players. When a gamma ray tags a dextrin molecule, it transfers some of its energy, causing the molecule to become excited and unstable. The gamma rays are it, and when they hit a dextrin molecule, they transfer some of their energy. This energy transfer can cause an electron to be ejected from the molecule, leaving behind a positively charged ion and a free electron. This energy can cause an electron to go flying, leaving behind a lonely and unstable atom. That's our free radical. These free radicals are highly reactive and can cause damage to other molecules in their vicinity. Scientists use a cool technique called electron spin resonance, ESR, to study these free radicals. ESR is a powerful tool that allows scientists to detect and characterize free radicals by measuring the magnetic fields associated with their unpaired electrons. It's like listening to the whispers of these tiny dancers. By analyzing the ESR data, scientists can gain insights into the behavior and properties of free radicals, such as their concentration, distribution, and lifetimes. ESR helps us understand how many free radicals are formed and how long they stick around. This information is crucial for understanding the potential effects of free radicals on biological systems and materials. And guess what? The number of free radicals changes over time after irradiation. Initially, there may be a high concentration of free radicals, but as time goes on, they gradually decay and disappear. It's like a dance floor that slowly empties out as the night goes on. The free radicals, once abundant and energetic, gradually lose their energy and become less reactive, eventually disappearing altogether. This information is crucial for understanding the long-term effects of gamma irradiation on dextrin. By studying the behavior of free radicals, scientists can develop strategies to mitigate their harmful effects and harness their potential benefits in various applications such as medicine, food preservation, and material science. Hold on to your hats, because now we're talking about viscosity. Viscosity is just a fancy word for how thick or runny something is. Think about honey versus water, for instance. Honey has high viscosity while water has low viscosity. Gamma irradiation can actually change the viscosity of dextrin solutions. It's like teaching the dextrin molecules a new dance move, the viscosity tango. Depending on the dose of radiation, dextrin can become more viscous, thicker, or less viscous, thinner. This change in viscosity is a big deal for industrial applications. Imagine you're making a glue, for example. By controlling the irradiation dose, you can fine-tune the thickness of the glue to perfectly fit your needs. Pretty cool, right? Section 4, Colorful Clues, UV-Vis spectroscopy reveals all. Get ready for some molecular detective work. Scientists use a technique called UV-Vis spectroscopy to study how gamma irradiation affects the chemical structure of dextrin. It's like shining a special light on our irradiated dextrin and seeing what colors pop up. When we zap dextrin with gamma rays, it can cause some interesting changes in its structure. These changes can actually make dextrin absorb different colors of light. It's like giving the dextrin molecule a new wardrobe. By analyzing the colors absorbed by irradiated dextrin, scientists can identify the formation of new chemical bonds or the breakdown of existing ones. It's like piecing together a puzzle, using colors as clues to understand the effects of gamma irradiation. Section 5. Feeling the heat thermal analysis after irradiation. Let's turn up the heat literally. Thermal analysis is like giving dextrin a lie detector test. It tells us how stable dextrin is at different temperatures and how it breaks down when heated. Gamma irradiation can actually make dextrin more resistant to heat. It's like giving the dextrin molecules a suit of armor, making them tougher and harder to break down. This enhanced thermal stability is a huge advantage for many applications. For example, irradiated dextrin can be used in food products that are exposed to high temperatures during processing. It can also be used in pharmaceuticals to improve the shelf life of medications. Who knew gamma rays could make things so durable? Section 6, a surface story. SEM zooms in on dextrin's transformation. Hold on tight because we're going microscopic. Scientists use a powerful tool called scanning electron microscopy, CM, to examine the surface of dextrin granules before and after irradiation. It's like taking a high-resolution photograph of a miniature landscape. Gamma irradiation can cause some dramatic changes to the surface of dextrin granules. It can create cracks, pores, or even smooth out the surface depending on the irradiation dose and other factors. It's like giving the dextrin granules a complete makeover. These surface changes can influence how dextrin interacts with other materials. For example, a rougher surface can improve adhesion, making irradiated dextrin ideal for use in coatings or adhesives. Section 7. The big picture, gamma rays, dextrin, and our future. So there you have it, a whirlwind tour of the fascinating world of gamma-irradiated dextrin. This journey has taken us through the intricate processes and groundbreaking research that are shaping the future of materials science. We've seen how gamma rays can create free radicals, change viscosity, modify chemical structure, enhance thermal stability, and even transform the surface of dextrin granules. These changes open up a myriad of possibilities for new applications and innovations. The transformation of dextrin granules under gamma irradiation is a marvel of modern science. By altering the molecular structure, we can tailor the properties of dextrin to meet specific needs, making it more versatile and valuable in various industries. But this is just the beginning. The potential applications of gamma-irradiated dextrin are vast and still being explored. Researchers are continually pushing the boundaries of what is possible, seeking new ways to utilize this technology to solve real-world problems. Scientists are constantly exploring new ways to harness the power of gamma irradiation to create innovative materials with enhanced properties. This ongoing research is paving the way for breakthroughs that could revolutionize multiple fields, from food science to pharmaceuticals to industrial applications. Gamma-irradiated dextrin has the potential to revolutionize numerous industries. Its unique properties make it an invaluable resource for developing new products and improving existing ones. Gamma-irradiated dextrin is not just a scientific curiosity, it is a practical solution with real-world applications. Whether it's enhancing the texture of food products, improving the stability of pharmaceuticals, or creating more durable industrial materials, the impact of this technology is far-reaching. So, the next time you see dextrin on a label, remember the incredible science happening at the molecular level. This seemingly simple ingredient is the result of complex processes and cutting-edge research. The molecular changes induced by gamma irradiation are a testament to the power of scientific innovation. By understanding and manipulating these changes, we can unlock new potentials and create materials that were once thought impossible. It's a testament to human ingenuity and our endless quest to explore the universe and beyond. The journey of gamma-irradiated dextrin is a shining example of how science and technology can come together to create a brighter future for all. Greetings to all our esteemed viewers. My name is Salah Lotfy from the Polymer Chemistry Department at the National Center for Radiation Research and Technology, part of the Egyptian Atomic Energy Authority here in Cairo, Egypt. I want to take this moment to sincerely thank each and every one of you for your incredible support and engagement with our channel. Your enthusiasm for science, innovation, and knowledge drives us to continue sharing groundbreaking research and insights from various fields. Your comments, likes, and shares are more than just numbers. They are the backbone of our growing community. Together, we are shaping a future inspired by curiosity and scientific progress. Thank you for being part of this journey. Stay tuned for more fascinating content, and let's keep exploring science together.